Hi everyone, welcome to our Crunch seminar. So today we have two talks. So our first speaker is Dr. Igor Halperin. Igor is an AI research associate at Fidelity Investments. He received a master's degree in nuclear physics from St. Petersburg State Technical University. And then he received a PhD in theoretical high energy physics from Tel Aviv University. His research focused on using methods of reinforcement learning, information theory, neuroscience, and physics for financial problems. And Igor has extensive industrial and academic experience in statistical and financial modeling. Prior to joining Fidelity, Igor worked as a research professor at NYU. Before that, Igor was an executive director of quantitative research at JP Morgan and a quantitative researcher at Bloomberg. So today, the name of his talk is Distributional Offline Continuous Time Reinforcement Learning with Physics for PDEs. So please join me in welcoming our first speaker.
Thank you so much for introduction, and thank you, George, for inviting me on this short notice. I'm very excited. That's actually my first talk ever given to the audience of machine learning researchers. My previous experience was only with physicists and people in finance. And also, this is my first work specifically on machine learning itself rather than on its application. So just to kind of a short background, I was involved in using reinforcement learning for quite a while, but so far it was more like I would call myself advanced user of existing techniques. But this work, well, I should say that it's a custom to say that this work would never appear without this and that. So in this case, I should say that this work would never appear without me getting across pins, and I'm very happy to be here in the in the land of pins, if I may say. And the background was that actually we've been working on implications of reinforcement learning. We were trying to apply it for some of our financial problems. And I was very unhappy with the performance of PPO, which people use. It's my understanding, it's one of the most commonly used methods. Somehow, like, it was too slow, too not robust, etc. So I started to think like how we can do it better. And then, fortunately for me, I came across George's papers on pins, and this is how it all started. So the rest was technicalities. Like when you have the idea, the path to the solution is simple. You just have to take all the solutions and remove those that do not work. All right, so the plan of my talk will be this. So first I will talk a little bit about continuous time reinforcement learning, why it's interesting. And then I will talk about what I called for short Dr. L, which stands for Distributional Offline Continuous Time Reinforcement Learning. And then, well, most of this talk will be math, and so I'll first talk about what I call soft Hamilton-Jacobi-Bellman equation, and then how we can, like, and here we will move on how we can use neural nets to solve it. And particular implementation, I like to call it Deep Dr. L. Also, the first time for me that I had an occasion to call something deep. So before, because so far I was my work actually did not use any deep learning at all. I was trying to stick to more like solvable things, but this is along the same lines. So this is what I like about this whole approach, is that it's so intuitive and so easily.
Igor, do you mind? Can you do a presentation mode, or so full screen? Or
okay, sure. Yeah, let me try to see it. Like, I usually like to have this thing on the side.
Oh, okay. We can see it. That's fine. Yeah.
Remember what
yes. I know what you mean. Yeah. That's fine. Let's leave it like that.
So let me quickly go. Like I think most of people in this audience are familiar with reinforcement learning, so I'll be very quick here. So in reinforcement learning, you have two sides to the game: agent and the environment, right? And the objective is to maximize your cumulative return. So this is the Markov decision process schematically. You have sets of states, you have sets of actions, transition probabilities, all this kind of thing, and the definition of the cumulative total reward. And as most of us know, the goal of reinforcement learning, of conventional reinforcement learning, is to maximize the expected total reward. So we have respectively two standard objects that we operate with. One is called the value function, which I call G sub t here, which is the expectation of cumulative reward conditional on the state only. And the other one is action value function, which is the same thing, but conditional on state and action. Right, and the task is to maximize these expectations, this expected reward, by choosing the optimal policy, and the optimal policy can be stochastic, can be deterministic in conventional, in standard control theory, or it can be stochastic, which is the common choice in reinforcement learning. And in discrete time formulation, we know that the optimal value function satisfies the Bellman optimality equation. So there is a Bellman optimality equation for the value function, Bellman optimality equation for the action value function. All right, so these are very commonly used standard thing. Now, what is used much less, I think, is continuous time reinforcement learning. And I want to talk a little bit about that. So, so in discrete time, which is the standard formulation, we know that the resulting equation is the Bellman equation, Bellman optimality equation, which is a difference equation. Now we may ask ourselves a question like, what's so interesting about continuous time reinforcement learning? Actually, George, it's interesting. One of the replies to my post was from she was not exactly my student, she was a student on my Coursera course, but she was a student of Marco Avellaneda, did her master with him, and now this girl started PhD in self-driving cars. And she was asking me these interesting questions, which I thought that the answer is obvious, but then I understood that the answer is not obvious at all to many people. So many people ask in robotics, in self-driving cars applications, why we should care at all about continuous time reinforcement learning. And so this slide is my attempt to reply to these questions. So I see many good reasons to look into continuous time reinforcement learning. So one, which is very obvious, is that like if you have a discrete time problem but with many steps, then proceeding to continuous time limit might be a good approximation numerically, right? Now, a little less obvious reason is that in many times you want to be flexible regarding your choice of time step, right? So you can say, like for financial applications, you can choose between, I don't know, intraday time steps versus daily time steps versus weekly time steps. So in discrete time formulation, every time you would need to solve different problems, which have no obvious connections to each other. But in continuous time formulation, they are all related to one another. So there is smooth transition between them. And in addition to that, very often our data is such that our steps or our sequences of actions are live on irregular, irregular lattices. So irregular time steps are can be better handled with continuous time formulation. So these are practical advantages, and there are also like theoretical advantages. So mathematical convenience. Unlike discrete time formulation, which produces Bellman equations, which are difference equations, in continuous time formulation, we end up with the Hamilton-Jacobi-Bellman HJB equation in the standard control theory formulation, which is a partial differential equation, PDE. Right, and once you have PDE, then you have a plethora of different methods that you can use. There are tons of numerical methods, so everything becomes accessible for you in this formulation, and in particular, of course, pins. All right. Now, on top of that, once you have the continuous time formulation, you can set it up in order to discretize again, but in a smarter way. So you may use implicit methods. You may explore different parameter regimes using that. So one of the issues with the discrete time formulation is that sometimes people implement it and then they see, in certain parameter regimes, it just blows up and they don't understand why. So having access to something like, PDE is generally very valuable in this formulation. All right, now, so that was about continuous time. Now, the other two components of this very long name in my paper, distributional, offline, etc. So I want to explain this as well. Now, why offline reinforcement learning? And what is offline reinforcement learning? So in offline setting, you do not have, the agent does not have access to the environment. The agent only has access to some historical data set. And this data set has a sequence of states, actions, and rewards. It might be collected by totally different agents using totally different policy, which might have nothing to do with the original objective of the first agent. So this policy is usually called behavioral policy. Now, why is it interesting? Because I think most of data that we have, finance for sure, is exactly of this sort, right? So you have previously collected data from trading or whatever, and that's all you have, right? It's very hard to come up with some sort of realistic simulator, at least for financial applications, because essentially making realistic simulator is equivalent in some way to having a right model, right, which is extremely complex task, right? So you can equivalently say, like, if you have the simulator, then you would, like, imagine that you have a perfect simulator, then you would take alpha 0 and train it like for a long time, and then you will quickly become the richest person in the world, right? Because it will beat all the rest of applications. But it's not realistic, right? So offline reinforcement learning is this typical setting, right? Now it's the formulation of offline RL is very universal, I would say, and in some way it can be viewed as a sort of extension of supervised learning. So in supervised learning, you take data and you convert data into patterns or labels or whatever. Like in a similar way, in offline RL, you take data and convert it to optimal actions. So I like to think of it as some sort of a Midas touch, right? So you take some garbage data and you convert it to gold, right? Ideally. So it all sounds great, but it's not as easy as it sounds, because offline RL is known to suffer from the most challenging issue with RL is what is called exploration error. So what is exploration error? In conventional discrete time or discrete state RL, If you use it offline, then the only data points which are available for you, the only combinations of states and actions are those which are in your actual data, and you have no option to try other combinations. So as a result, an offline RL algorithm can assign unrealistically high values, high reward values to some combinations of states and actions which are unseen in the data. And this is called exploration error. And on that count, clearly, continuous time, continuous space formulation based on PDE sounds like a principled way to address these exploration errors. That's why I initially started to think about that. Now, the other component is distributional RL. So what is distributional RL? Traditional reinforcement learning only controls the expected return, the expected sum of future rewards. And well, it's done this way because it's easier to do it this way, but it doesn't mean that it's optimal to do it this way, right? So in finance, for example, no one takes decision based only on expected returns. You would quickly run out of money if you do it this way. So you have to control into account risk, right? And in the language of reinforcement learning, risk is uncertainty about your returns, right? So there are ways to control uncertainty of returns in reinforcement learning, and there are two approaches. One is called risk-sensitive RL, and another is called distributional RL. So both of these approaches, they take sample-based approaches such as TD, time difference learning, to control the whole distribution of return. Now, what I will be presenting in this work is a different view of controlling uncertainty, which is based on a probabilistic approach and PDEs. All right. So now let me.
Igor, I have a question here because we're trying to. Can I ask a question here about because you sort of think of uncertainty in a certain way, a risk. But what's the source of uncertainty? Is it specific to sources of uncertainty, or is it some uncertainty here? You mean lack of knowledge, basically?
Oh, no, sorry. Yeah, I was not very clear. It's actually not uncertainty. Yeah, if we want to be more accurate, there is a big difference. Thank you for correcting me. I like to make this point myself, actually, but I just forgot. There is a big difference between uncertainty and risk. So here we're talking about the risk, actually. So here we're talking about control of the distribution of returns, right? As opposed to only controlling the expectation of the return. So that's, yeah, it would be better to say. We in distributional RL and risk-sensitive RL, we care about higher moments of return distribution and not only about its mean.
Yes. Okay.
Right?
Thank you.
Yeah. All right, so now let me get to the math. So this is how I like to state this problem. So we work in continuous time RL, as I said, and in continuous time formulation, the main modeling object, or one of the main modeling object, is the running cost. So running cost, okay, I have to say that I choose the control theory based view of this. So instead of maximizing rewards here, I'm equivalently talking about minimizing costs. All right. So if you have running cost, which is the function of state S, X, and actions A, then my prime modeling object would be the cumulative cost, which is the time integral of this running cost with this funny discount factor, but this funny discount factor is needed because I want to recompute everything relative to time zero. Okay, so this is my object, right? So and I imagine that I start my control at time zero. My time horizon is capital T, and my running time is small t, right? So at each time small t, I have this object, and clearly it depends on the future. right? When small t is less than capital T. Therefore, it's a random quantity, right? But what we can do, we can split this random quantity into something which is already measured, which would be the integral between 0 and current time t, and the remaining part, right? And I call this first part capital C. So capital C would be realized cost, which is realized up to time t. And what I want to do with that here is I want to extend my state space. So initially my state space was X, right? Now I find it convenient to extend this state space to by including this running cost C, C sub t. So, and if I add to my dynamics also the actions, then I would say that now we have the Markovian dynamics in extended space, Y and A, where Y is this combination. So it's extended vector of X. So I will be interchangeably using in my slides both these variables, but please remember that whenever we use this Y, it's actually just this extended vector, right? Okay, so so now how does the task look in this formulation? We in traditional risk-neutral reinforcement learning, we are concerned with minimization of the expectation of this cumulative cost, right? So now if we take this formula, plug it back this expression, then what we see is that because expectation is the linear operation, clearly this is just an additive function of the running cost, right? As you can see from here. And obviously from this expression, the partial derivative of your value function would be 1. And this is actually like I was asking myself, okay, if this is the useful quantity, why it doesn't appear in a conventional formulation? And this is the reason why, because it's completely trivial. No one cares about this additional state variable in this formulation. But if you do distributional RL, then it does become full-blown, variable, state variable, right? So how we do distributional RL? Instead of minimizing just the expectation of your running cost, we minimize the following cost functional. So we say there is so now our prime object, one of the prime objects becomes this probability. So what is this probability? This is probability to have the total cost at time capital T equal to Z, conditional on starting your system in state YT, right? And then integrated with some function, which actually gives you kind of the amount of your preferences for having smaller cumulative cost versus higher cumulative cost. So I call it negative utility because it's kind of something that you want to minimize. And my assumption is that it's a convex function with the minimum at 0. So in my experiment, I simply use the simple quadratic function. All right. Now, and this functional actually does what the distributional RL or risk-sensitive RL do. So it controls the whole, it tries to control the whole distribution of returns rather than just expected returns. And in this formulation, as we will see shortly, dependence on this realized cost will become non-trivial. All right. Okay. So before proceeding, I want to do something that is conventionally done in discrete time. In maximum entropy reinforcement learning, the cost function, which I showed here, which is now here, would be regularized. So I consider regularized cost function, which is regularized by time integrated KL divergence between my unknown, between my optimal but yet unknown in this stage policy, and some prior policy, which I call which is behavioral policy in this case, which I call PI-0. All right, and there is the some coefficient here. So this parameter is traditionally called inverse temperature, and is traditionally introduced in this way as 1 over beta, so that in the one regime, which is called low temperature regime, when beta goes to infinity, then this term drops. And in this case, we cover the classical AGB control with deterministic policies. But in the opposite limit, you can also consider opposite limit when beta goes to infinity, and then this term becomes dominant, right? So your optimization would not care anymore at all about this term. And the optimization of this would produce you that pi is equal to pi-0. So which means that in this opposite limit, the agent doesn't do any optimization at all and sticks to the behavioral policy. And obviously for intermediate values, it chooses something in between. All right. Now the optimal cost function is introduced the same way as in discrete time RL. So I use the notation without the index pi here. So I call this this guy would be this notation would be used for optimal value function, which is defined as the minimum of this expression over all policies. Right. So we want to find this function subject to terminal conditions, and terminal conditions are actually very conveniently are done by given by this expression. So what one thing that you can notice here is the terminal condition is actually only a function of realized cost, but not the x, which is just an observation. I don't really use it. But what is important here is that this utility, this preference for different risk expressed by this negative utility function, only appears in the terminal condition in this formulation, right? Which is the way we used to have with PDEs, but it's different from what people normally have with risk-sensitive RL approaches, where it usually appears for intermediate states as well. So here the only difference between different versions of the model for different utilities will be due to different terminal condition, right? And then what you can do with this, you can follow the traditional derivation of the Bellman equation with this cost functional. And by taking the continuous time limit of this equation, you will recover what I call the soft AGB equation, soft distributional version of the AGB equation. Now, I'll skip the derivation. It's pretty straightforward but technical, but I would like to give you a flavor of how it's done. So my assumption for the underlying process is of multidimensional diffusion. So for a given action, my state variable undergoes multivariate diffusion. So here's the drift term as usual, and there is the diffusion term. WT is the standard n-dimensional Wiener process. And in this formulation, the action A is random, right? Now, if you look at the derivation of the AGB equation itself, so AGB equation, then you'll see that actually what enters this equation is not that diffusion equation, but rather its controlled version. The controlled version is obtained when we take expectation of the right-hand side of this equation over actions A using some policy pi. And this controlled diffusion now reads like that. And in this controlled diffusion, the drift and volatility terms will be related to this drift and this drift by these expressions. So we just have to take averages, right? All right. Again, skipping the derivation, I'll just give you the kind of final expressions. You can, if you use fixed policy, then this line of reasoning will produce you a backward Kolmogorov equation for the cost function with fixed policy, which has this form. So I apologize for a little bit broken fonts here. This circle denotes actually so this is the multivariate formulation, and this guy is the Hessian, right? So this circle denotes a sum over indices I and j of this matrix times the Hessian of this. But I just use it for compact notation. So now this backward Kolmogorov equation is pretty much conventional one, except maybe for this additional first derivative, which is due to my additional state variable c. All right. Other than that, it's a conventional Kolmogorov PDE regularized by the KL divergence here. Now, using conventional roots again, we can now maximize it, or actually minimize it, because we minimize cost. We can minimize the right-hand side of this equation with respect to all policies. It can be done semi-analytically in terms of the cost function and its derivatives, and then if you plug back this expression into this original equation, then this equation will take this form, which is shown here. All right, so this would be a soft distributional HAB equation in the most general form. And what you can see here is that in this form is just some sort of integral differential equation, which is not very easy to work with. Maybe it can, but I didn't try. I just wanted to simplify it further. Now, how we can simplify it further? By doing a few more things. So one of these things is I use a specific Gaussian mixture model for my behavioral policy, which I think is perfectly fine in the general case, because we know that the Gaussian mixtures are universal function approximations, right? So no big loss of generality is done at this stage. And this would be my specification. So just a mixture of normal distributions. You can have means of your components, which are some non-trivial functions of the state. In my numerical experiments, which I'll show below, I, for simplicity, took them as just constants, right? And that's the specification of the behavioral policy.
And Igor, sorry,
yes.
Igor,
Yes.
what? Just give us an idea of what capital K is, what values.
Well, in my because my purpose was just to proof of concept. I use the simplest version of k equal 2 in my examples, but okay. It can be anything really. Yes. Well, if you ask like specifically for financial applications, I don't think that something more than k equal 2 or 3 is ever needed. That would be realistic choices.
And how about the PDE? In what dimension? In how many dimensions?
PDE?
Yeah, the PDE you show us.
Well, PDE I'll show you like 10 and 100 dimensional examples.
Okay, that's what I wanted to know. Okay, yeah.
Yes,
Okay,
right.
great. Yeah.
Right. Now, what might be a little bit more restrictive is my choice of the dependence on the actions in cost and in drift. So this choice is actually a very standard choice in the control literature. It's called the linear quadratic dynamics, right? When your dynamics is linear in your actions, like here, and your cost is quadratic in your actions, like here. Now, in a more general view, you can always think of expressions like that and like that as simply, first order Taylor expansions of more general functions here and here in powers of A. Right? But the important point which I want to make here is the following, that normally people use this specification for deterministic control. And if you do it with deterministic control, then basically with this specification, you lose all, non-quadratic effects in your dynamics. But in this setting, I'm working with stochastic policies, and therefore, with stochastic policies, non-linear effects can be captured kind of in stochastic scenarios, probabilistically. They can be mimicked. So I don't think there is a big loss of generality with this choice. But for those who want to try this for like more complex specifications, it can be done like recursively. One way of ways of doing that. But anyway, that was my choice. So these two things are actually what makes this integral differential equation more tractable and brings it to the final form that I use. All right. The other advantage of this choice is that with this choice, so this is the behavioral policy, but my optimal policy will also stay in the same class of Gaussian mixtures with this choice, which is very convenient. And actually the formulas are shown here. So, so before, clearly like the sequence of actions is here is like in classical formulation. I need to solve the PDE for the value function, and this PDE gives me the optimal policy. The difference is that in classical formulation, the optimal policy is deterministic, but in this case, the optimal policy is stochastic. What does become dependent on the optimal value function are coefficients in this Gaussian mixture, right? So weights become dependent on the optimal cost in this way. So this is a very nice expression, but only after you use some compact notation for things which enter this equation. So I called those expressions Hamiltonians for very specific reason. So those Hamiltonians define how the weights in your Gaussian mixture transform from behavioral policy to the optimal policy. And the reason I call Hamiltonian because this looks like the Boltzmann distribution in statistical physics. Now, in addition to changes of weights, also the means change, and this is the analytical expression for the means. All right. So now, with this specification that I showed in the previous slide, the previous integral differential equation becomes a semi-linear PDE, and this semi-linear PDE is shown here, which is already more tractable, right? Which is already something that you can almost directly use with pins, right? So this is a semi-linear PDE, and it should be solved under the terminal condition, which I already showed before. Now you can track how this semi-linear PDE transitions into something known, into the classical HGB framework. And for this, you have to take the low temperature limit, beta goes to infinity, so this thing drops, right? And in addition, if you want to recover the previous risk neutral formulation, which I mentioned before, right? Traditional formulation, then if you remember what I was saying in the first slides, this would correspond to taking these partial derivatives to 1. Right, so and in this way, like these two changes will recover the classical stuff from this. But for more general choices of beta, this serves as a regularization. You can also consider the high temperature limit of this equation, where this term will be dominant. All right. Now here comes the difference between how I treat this relative to pins. So unlike pins, I do not directly encode this into the loss function because of high dimensionality. Right. Instead, I use something which is more close to what people do with the simulation or pathwise based approach to PDEs. And they call it forward-backward stochastic differential equation. So how does this thing work? Usually people use it in a setting or in a model-based setting or in simulation setting. And they operate with two stochastic differential equations. So one of them, the first one of them is just the dynamic equation. And for my setting, it will be the same equation, the same controlled diffusion, which I showed you before. I just write it in slightly different way to emphasize the dependence of this controlled diffusion on your cost function, which is still unknown, right? So controlled diffusion is shown here. This is the forward. It propagates forward in time, forward dynamics. And there is the second equation, which is actually a backward stochastic differential equation. Why it's backward? Because it's determined by the terminal condition. It should be solved backward in time. And the second equation is obtained by combination, by combining Ito's lemma and the backward Kolmogorov equation for the cost function. I'll skip the derivation. It's simple, but what it produces is this. So if you combine these two things, that you get this equation, right? So this pair of equation is a particular case of more general approach called FB-SDE, forward-backward SDE approach. So usually people just work with these equations by simulating paths of Brownian motion. But now my setting is different because my setting is offline RL. And initially I was thinking, okay, maybe it means that I should somehow recover the path of Brownian motion for my setting. But then I realized it's not needed. Actually, what should be done here is just you can eliminate, using these two equations, you can eliminate Brownian motion. You can think that your data corresponds to some realization of Brownian motion, but you don't need to compute, kind of recover this Brownian motion. You can just use these two equations and combine them together. And if you do it this way, then you will put it in a very nice form, which actually kind of, to me at least, is reminiscent of classical mechanics. And it takes the form of the Hamilton-Jacobi equation this time, not HJB equation, but rather HG equation in reverse time. So combining these two will give you this equation. It's you can think of it as a pathwise dynamics on realized paths, where this operator I call it effective Hamilton-Jacobi Hamiltonian. Maybe not the best form because Hamilton appears twice in this, but I didn't have any better way. But anyway, this is the expression of your pathwise dynamics, right? And we almost done. I don't know how much time we have left. I'm trying to go quicker.
No, Igor, take your time. We
right.
Yeah.
Okay. All right. Perfect. Okay. So this is one element. So like. This is the tick of the game, which I will try to explain, because this is I think the kind of new element, one of the new elements here, right? So first thing, I take realized offline data, right, and I convert it into this equation, right? So this equation expresses the dynamics on realized paths, if you wish, right? And this equation, as you see, it relates the cost function with this right-hand side, which depends on the derivatives. So derivatives appears here, but they're also implicit in this expression. I didn't show the explicit form for this guy. You can see it in the paper, but it's something that depends on the cost function and its derivatives. All right. Now here we come to the interesting part. I mean, another interesting part. All right. So usually people who work with these forward backward SDEs, as I mentioned, they actually don't do RL. They rather do you can call it model-based RL if you wish, but they solve the equation using a known model, right? Here, my interest was in learning the optimal cost or learning the HGB equation, its soft version from data, right? But here we can ask a question like, what does it exactly mean to learn this HGB equation from data? Because naively, we would say that we need to observe optimal data to learn the equation from data. And the problem is that we're not given the optimal data, but we're rather given behavioral data. So the question is how we can proceed. And like conventional standard offline approaches, RL approaches, they use value iteration or policy iteration. But here, due to the beauty of PDE formulation, there is a way to completely sidestep this. So to express loss function in terms of one function only. How? Using exact likelihood ratios. And this is where the advantage of this formulation of these linearized dynamics come. So in this formulation, I can exactly compute the likelihood ratio of two trajectories. One would be the behavioral trajectory. I call it, not trajectory, this is just for one-step transition probability. So if I have two transitions between fixed values x sub t and some new value x sub t plus delta t, then I can compute the likelihood ratio of this given fixed transition under different scenarios. One scenario is when I act optimally and apply policy pi. And another case is when I just follow the behavioral policy. So this ratio can be computed analytically, and the expression is, it's not fully explicit expression because it depends on these guys, but I refer you to the paper for the dependence of this thing on the cost, right? But the point is that this is a quadratic function of this guy, actually, of the expected value of the action under policy pi. It's an analytical expression that involves the cost and its derivatives. And now it's different from what people usually do in the context of stochastic control, because over there they rely on the Girsanov theorem, but it's completely equivalent to Girsanov theorem, just rewritten in terms of realized values. It's more convenient to do it this way when you deal with the offline learning. And now we have all the elements which allow us to do this magic. What would be the magic? The magic would be to have one single loss function, which is trained directly from data, and does the policy optimization in one step, not in many steps, in one step, right? How we do this? We use these two elements that I just showed, right? So we treat the behavioral data as optimal data by tweaked by the this exact likelihood ratio, which has an analytical expression, and which gives you this term in the log likelihood. And we have this expression. This expression is basically obtained from this formula. So when we implement this formula using neural net as a parameterization for your optimal cost, then I basically add in the right-hand side some error term here, right, with some parameter eta square, and this gives me this term. So this term is the model mismatch, is the model error, and this term will be the data error, mismatch of between the model and the data, but not the data itself, rather the data interpreted internally by the model according to its view of what should be the optimal cost, right? So this is the log likelihood. Now I just take the log, flip the sign, and rescale it for convenience by this parameter, and this is my final expression. Okay, this final expression, as advertised, it involves only one function, right? And what it achieves the stated goal of converting offline RL into straightforward supervised learning problem, which solves it in one step and doesn't involve any policy or value iteration. All right. Now here I wanted to quickly go like so. It has so this approach is similar, is more similar to pins rather than to FBSDs. But it shares similarities with both and also different from both. So the similarity of this approach with pins is that, like pins, this approach uses a single neural network for the whole solution. And also, like pins, it produces the solution for arbitrary inputs, so you can extrapolate. The difference is that pins normally, like they deal with general PDEs and they use mesh, some sort of a mesh as far as I understood. Here, instead of mesh, I just use behavioral data, which is already available for me, right? And also the other difference is due to the nature of the problem. We don't, like in this formulation, I don't have explicit boundary conditions. I like HGB equation is like natural boundary condition. I don't have to enforce them explicitly, and therefore I have smaller number of hyperparameters, essentially just one hyperparameter, this one. Also difference and similarities to forward backward SDEs is like the similarity is that it uses stochastic pathwise formulation. This approach in order to get better signals for training. The difference is that it uses a single neural network, which is like pins, and also produce the solution for arbitrary inputs, which is also like pins. All right, now I'll move to examples. So in the paper, because my focus was on the proof of concept rather than on exploration of efficiency of this, I just decided to show two examples with simulated data. And the setting was actually kind of, I chose this number of steps, this number of, oh, sorry, there is a typo here, it should be five-dimensional action space. Dimensionality of action space, time steps, and state space was kind of in the ballpark of what we have in mind for financial applications. But I also like explored the second example would be kind of more high dimensional. So anyway, my first example is I simulate 10,000 trajectories in 10-dimensional state space and 5-dimensional action space. I have two components of my Gaussian mixture and 40 time steps. I use a very simple like constant specification for my drift functions. So my drift is just the linear function of the state, and the other function also has the linear function of the state. The cost functions are defined this way, right? So I simulate a bunch of trajectories. I just show a randomly selected subset of this. The reason I show this is to emphasize the range of simulated values, right? So I only show you 100 paths out of 10,000 paths, but most of them also kind of produce bounded values of parameters around the same values, right? Then I train this thing, and training is actually pretty fast. So I have pretty old MacBook, only 2.5 megahertz, and still it took about 8 minutes of training for 30 epochs here. So here's the negative log likelihood as a function of epoch, and the right-hand side is the training schedule, my learning rate as a schedule. So it does seem to produce something, right? And to explore what it actually produces, I plotted the computed means of my Gaussian mixture for the optimal policy using my optimal value function, right? So because I have two components of my Gaussian mixture, respectively this graph and this graph. And for each one of these graphs, I show all 5 components of my action. So those are means, 5 dimensions of the means of the Gaussian policy, as a function of randomly choosing component of X state. So it's the same component that I used here. I also used as an x-axis here. So the most interesting fact here is that, as you can see, this guy is able to extrapolate, not just interpolate, but extrapolate. Those policies asymptotically approach constant values. And I remind you that here the range was very limited, right? So it was so the demonstrated range was somewhere here. Nevertheless, the model is able to learn the function and its derivatives and extrapolate, which is very valuable, which is exactly what is needed in offline RL. All right, so this is 10-dimensional example. The next example is 100 dimensions. And I basically stick to the same parameter specifications as here. I just rescaled a couple of them in order to have the relative balance of different terms similar to this example, and kept the rest of parameters the same. So this time for 100 dimensions, it took me about 45 minutes to learn for 30 epochs, right? And again, I look at what it implies in terms of the policy. And again, I see the same picture, right? So this thing is able to extrapolate, which is something I think highly valuable. All right, so that would be my summary. So this approach, which I call Dr. L with Sci-Fi RL, amounts to solving the soft HGB equation from data directly. It reduces offline RL to supervised learning, and then solves for optimal policy in one step. There is no value or policy iteration involved. It controls the exploration error of offline RL using, I like to call it regularization by PDE, which is essentially what it does, right? Now, like my very limited experiments showed as a proof of concept that it's able to learn in minutes, not in hours or days, using pretty moderate amount of data. 10,000 trajectories even for 10 dimensions is not much, but not to say about 100 dimensions. So I think that 10,000 trajectories is a moderate amount of data in this setting. And this approach can be extended in multiple ways. So it can be applied for online RL as well, using kind of experience replay type of approach. It can be extended to non-quadratic dynamics if you want or need, by putting this whole thing in some sort of a loop. And while initially it was developed for financial applications in mind, which is what I do, I hope that this approach can also be used for other applications, robotics, self-driving cars, etc. Here is the reference to the paper, and here's some extra something that has to do with the phi component in this sci-fi stuff. This is just the last chapter from our book that we published the last year, and it talks at length about different connections between machine learning and physics. And I would like to end up on this point, and sorry for running over time.
Thank you very much, Igor. We have almost 60 people attending today. That was great. And is the code available, or is it owned by?
The code actually is not available because I did it on my work laptop, and it's like, you know, once something is there, it's hard to get it out. But the code is easily reproducible, I would say. It was like I can like, if anyone is interested, I can explain what I did. I just took one of the libraries for neural PDEs and hacked it, replaced the loss function by my loss function.
Yep. Okay, yeah, we are interested in applications in biomedicine, and one of my questions, and then I will ask other people to ask questions, was you use 40 steps.
Yes.
What's the cost with a number? If I want to do 1,000 steps, what's the cost for it? How does it scale?
Whoa, good question. I didn't try. I didn't try. But is it like, this is like what you would be interested in, like 1,000?
No, I want to see a longer term integration. Yeah.
I see. Yeah, I can try and let you know. I didn't so far.
Okay, we have lots of experts in the audience on Hamilton, Jacobi, Bellman.
Oh, that's great.
So I don't know if, but I don't know if Jerome is listening because he was traveling. But
yes, yes, I've been listening. I mean, thank you very
Jerome
much.
is here. Yeah, Jerome. Yeah.
I am a strong believer of solving Hamilton-Jacobi PD in high dimension. As you say, there is no iteration of value policy and so on. But my question is, I know it's general, but important. I do understand completely the fact that we are using linear dynamics and quadratics. What prevents, according to you, so if we change the quadratic by non-quadratic, we lose the closed form that Gaussian remain the Gaussian and so on. So is it because of this lack of closedness that people do not go beyond the quadratic?
Yeah, I just wanted to kind of, at least as a first cut, I wanted to kind of stay as close as possible to, you know, analytical formulation. But if you use non-quadratic, then okay, let me refer you to this equation, right? So,
yes,
you know, this is the most general formulation, right? Now, if these guys and this guy is not linear or quadratic, but this thing is quadratic, then obviously it's not solvable anymore closed form.
Yeah.
So what people do, like they iteratively linearize. This is one possible approach, right? Which is something that you could do here as well.
Yeah.
So this is what I meant by saying that you could put it in a loop.
Yes. Yeah. And I see. And my other question is, when I see those formulas, I mean, they should be used in the design of the architecture of the network, because I think that here we have a lot of structure that could be leveraged into the neural networks that you are using in pins.
Igor, what Jerome means that you can take some of these elements that you see in the equation and hardwire them. Change your architecture. Don't use standard architecture. Change your architecture to inspire. That's why I think he has a couple of papers on that with Tim Wei on how you can use Hamilton-Jacobi and to affect the architecture itself.
I see. I have to admit I didn't see them, but I would be happy to take a look. I didn't like what I did was very straightforward. What I did for these experiments, actually, I just took a feed-forward neural net, very straightforward, 3 layers, 3 hidden layers, 100 neurons each layer, Well, I should. Well, what I do want to mention is this part, which kind of pleasantly surprised me. So you see that these guys are super smooth, right?
Yeah.
It was not the case initially. Initially, I used a different activation function. So I used a library. I can send you the link. I used the library put by someone called Nunks, I think. Whatever. It was PyTorch-based library, which I just hacked. As I said, I replaced the loss function. But initially, those guys used, for whatever reason, they used the sinus function activation. And this initial activation did not produce as smooth curves as shown here, right? So when I decided to try different ones, I tried hyperbolic tangent as everyone, which was also kind of not ideal. But when I tried soft plus, then this produced these very, very smooth curves. I don't know why, but that was the. But other than that, I mean, like there was no other customization. So just take the feed-forward neural net and
Igor, we work with adaptive activation functions. One of the postdocs here, Ameya, has developed different types of adaptive activation functions. So the data, you can parameterize the activation function. The data will tell you. So each neuron could have its own, or each layer could have its own. Yeah, so they fire at the different rates and so on. So that solves some of these problems. But let me ask if Ting Wei or Yang Liu, who are also working on this, have a question, or Jen Jan.
Hello. Hi.
Hi.
I'm Ting Wei, and I want to ask you a question about the loss function. Oh, by the way, this is very interesting, and I will look into the paper to see the details. Can you go to the loss function?
Yes. Let me see, where is it? This one? Yeah, it's the same.
Intuitively, I can see there are two terms, and it seems the first term is like HJPDE.
Yes, this term is the model error, right?
Yeah, but can you explain more about what's the meaning of the second term? What's delta S?
Yeah, absolutely, of course, right. So there are two terms in this loss function. The first term is this first term is actually what is obtained from this guy, right? So this is the exact equation, right? In a sense, right? When I use neural net in order to represent the solution of this equation, I just add some errors on here. So I would say that the change of my value function is given by this expression plus some error. This error I wrote as this error I wrote as eta times random times noise, right?
New. We call new.
New. Sorry, not eta. New. Yeah, I meant new. Right. So and then the error, like then it gives me this term in the likelihood, right? So this is the model error, right? Error of my fit of my neural net as the approximation of the solution. The second term is actually what comes from this likelihood ratio, right? So this is the trick, right? So because it's all based on PDEs, I can say, oh, I just take behavioral data, but I look at this data differently. I look at this data as tweaked optimal data, right? Tweaked by this guy. And this guy, as I showed you before, it involves this exponent. So this expression delta S is an analytical expression which involves my value function and its derivatives, right? This is the trick which allows me to have this. So this ratio is represented by this term. It's a log of this.
Yeah,
that's the loss function. So it's a penalty. It's a combination of penalty model mismatch versus mismatch of model relative to the data interpreted by the model. reinterpreted by the model.
Right.
Yeah, thank you. Yeah, I will try to look into the paper. Maybe we can have some more structure in the neural network and see why the softmax works better than the other activation function. Well, thank you for this interesting talk.
Yeah, thank you. Anyone else has questions? It's very interesting, Igor. Very interesting. As I said, we're interested in. We also work on something else we call functional priors. We haven't published that yet, but basically with functional priors we extrapolate, like you show, and we have this concept, but we don't have the optimality. So, but it's really interesting. We have a huge extrapolation ability also, but we will. I'll send you a preprint when we are ready to release it. Jan Lu, do you have any comments?
Okay. So this is Liu. Actually, okay, I don't really have any question directly related to this work, but I want to ask Igor if he has like some idea on what if we. I mean, I'm always thinking about like this. So we are working on some physical environment, so that the environment could have some. I mean, this is kind of like very general stuff. I'm not sure if you properly ask here. The environment have some physical laws in the environment. I don't know. And for this kind of problem, because when I first read about the title, field-informed reinforcement learning, I think about, well, can we incorporate the physical knowledge into the learning algorithm? But in the end, I realized that okay, he didn't really use the physical laws in the environment, but instead using the Hamilton-Jacobi-Bellman equation. So I mean, so may I ask you, Igor, have you seen about this kind of problem? Yeah, that's it.
Igor, for example, I think what he means, if you have like, let's say, a 3D printing facility we try to control, or a digital twin, or a robot that you said, the robot. And obviously there we have kinematics, we have momentum conservation, we have mass, we have all that stuff. Would that replace your behavioral type of data? How would you?
I see what you're asking. Yeah, yes. That's a great question. It's not only in robotics. In our actual applications, we have the same.
Yeah.
You asking, well, at least part of your question, I think, is about like additional constraints. I'm not sure if I have to think about like if you have additional like conservation laws like in physics, what of those translates is already encoded into HAB equation and which are not. It's a good question, but if we're specifically talking about constraints, I'm not exactly sure what kind of. Definitely, like one simple way to modify this formulation is straightforward, right? So you can just add constraints as penalties, right? Directly into loss function. The other approach would be because it's all a continuous state formulation, right? Continuous state, continuous action formulation, and I use KL divergence. We know that the measures in KL divergence should be equivalent, which means that if my prior distribution is 0 somewhere, exactly 0, then my posterior will also be 0 there. So I can enforce constraints, at least some constraints, by kind of simply by specifying my prior distribution, right? So if, let's say, I want it in a band, along all dimensions, I can just use some truncated distributions, right, which put 0 weight outside of this band, and then I will be guaranteed that my posterior distribution will also satisfy these band constraints by construction. How universal it is, I'm not sure. How to compute those integrals, I'm not sure either yet. But it can be, maybe it can be doable this way.
Okay. Thank you. Yeah, that's kind of reasonable.
Igor, thank you very much for taking the time today. Let's see, 10 years ago, I was in Leningrad, St. Petersburg. It was such a beautiful, I can't wait to go back.
I was born there, actually.
Yeah, I know. I just this is like the Venice, of course, the Venice of the East, right? So, but thanks for taking the time today. We have to go on with the second talk on some different topic, but I would follow up with you because we're really interested in a couple of applications I have. So,
absolutely, I would be very interested to kind of continue conversation, and I was looking actually for some sort of interaction with real machine learning community, like, because so far I was working mostly.
Yeah, so we're also not very far. It snows here. I don't know if it snows in Connecticut today, but in Boston it snows.
Yeah, it's very cold today.
But thanks again, and Minlang, please, you can start the second part.
Thank you. Thank you.
Is it something I can stay or?
Yeah, you can stay. We'll talk about the DeepONet, this thing that the operator regression.
Oh, I see. All right. Okay.
Instead of functional regression, operator regression. Yeah.
Mm-hmm.
All right. Thank you, Igor. Thank you so much for your interesting talk. So let's move on to our next talk. So our next speaker is Somdatta Goswami. Somdatta received her PhD in structural engineering from Bauhaus University, Weimar, and she joined our group this year. So today she's going to give us a paper review with the title, Learning the Solution Operator of Parametric PDE with Physics-Informed DeepOnets. So please join me in welcoming Somdatta.
So today I would be actually reviewing the article, Learning the Solution Operators of Parametrical PDEs with Physics-Informed DeepOnet. And this article has been authored by Sifan Wang, Hanwen Wang, and Paris Perdicaris. Currently, this article is available on arXiv. To introduce the topic, so firstly, the parametric PDE problems that involve the learning of solution operators that maps the variable input entities to the corresponding latent solution of the underlying PDE system. Now, these kind of problems get really difficult to be solved using traditional tools, like traditional numerical tools, like finite element and isogeometric analysis, because it involves a huge amount of cost, as all these simulations, an individual simulation involves the computation and the recomputation for different domains, geometries, input parameters, and initial boundary conditions. This gave rise to to machine learning approaches. Now, neural network is a popular machine learning approach which represents the solution map of the parametric PDEs as an integral of the Hilbert-Schmidt operator, whose kernel is parametrized and learned from paired input-output observation. Even though the neural operator methods are resolution independent, but they require a large amount of training data sets, which involves this kind of implementation often involves slowing computational speed and the involvement of expensive training loops. A better approach to this problem was proposed through DeepONet, where the solution solving the parametric PDEs by learning the solution operator was proposed. Now, these operators could even be nonlinear operators. This approach maps between the infinite dimensional Banach spaces. DeepONet still requires a large amount of annotated data sets of paired input-output observation. But an improvement was that the model was simple and intuitive, the architecture of the model, and it was faster to train it while allowing a continuous representation of the target output function that is independent of the resolution too. This approach could circumvent the curse of dimensionality that is involved in solving engineering problems. Now, the extension of the DeepONet framework. What was required to be addressed was that using a large amount of input-output paired training data set was very expensive to obtain. And also the predictions of the predictions obtained from the neural network might not satisfy the physical laws, the governing physical laws like the constitutive equations and the constitutive laws in the observed data set. Now, what was recognized as from the outputs of the DeepONet was that the output of the DeepONet model were differentiable with respect to the input coordinates, therefore allowing to use the automatic differentiation operator technique to formulate an appropriate regularization mechanism for biasing the target output functions to satisfy the underlying PDE constraints. This concept was motivated from physics-informed DeepONet, a physics-informed neural network. Now, the physics-informed DeepONet was imposed with a thought that the underlying physical laws would be satisfied via soft penalty constraints during model training. And also, this approach does not require an input-output paired observation like the conventional DeepONet. The benefits that were observed are it had up to 1 to 2 orders of magnitude reduction in the predictive errors. It enhanced the generalization performance even for out-of-distribution prediction and extrapolation tasks. And the data we could say that the data enhanced data efficiency as no paired observation was required. Now, all these 3 benefits have been shown through various numerical examples, which I'll show later on. Brief overview of DeepONet. So let U, V, and S be a triplet in the Banach spaces where we represent a parametric PDE of the form N in U and S to be equal to 0, where U denotes the input functions and S denote the unknown solution of the PDE. Now, subjected to appropriate boundary condition, there would exist a solution S, which is S of U in the domain of U. Now, if the solution map defining the solution operator G is like G of U should be equal to S of U. Now, the solution map is represented by an unstacked DeepONet, G of theta, and where theta would be the trainable parameters of the neural network. Now, G of theta is basically a prediction of the function U, which is evaluated at Y and is expressed as a dot product of the output from the branch net and the trunk net, which is represented here. To obtain the parameters theta, we minimize the loss using the mean square error. And here, N is the separate input functions, which is sampled from U, and P denotes the locations in the domain where we want the predictions in the domain G of U. This now we would understand this through an example of the problems that is associated with DeepONet and the solution that was proposed through physics-informed DeepONet. Here we would be using a simple initial value problem to understand the we'll learn the antiderivative operator, which is the derivative of S of x with respect to x is equal to U of x, where x is defined in the domain 0 and 1. This has an initial condition on S, where S at x equal to 0 is 0. Now we want to learn this antiderivative operator. To generate the training data set, 10,000 different functions of U from a zero mean Gaussian process prior with an exponential quadratic kernel with a length scale parameter of L is equal to 2 are randomly sampled. The corresponding 10,000 ODE solutions were obtained by integrating the ODE using Runge-Kutta method. And for each pair of U and S, 100 sensors were chosen, which were uniformly distributed over the time interval 0 to 1. And randomly, we select P equal to 1 observations for the observations on S in the domain 0 and 1. Sorry. To generate the test data set, the same procedure is repeated where Q or M from the previous slide is equal to 100 and P is equal to 100. So in total, we have 100 cross 100 cross 100 data. Now the final data set contains 1,000 different samples of the random input function U. The network architecture that was followed is that 2 hidden layers with 100 neurons was used and the rectified linear unit activation function was used. Using the Adam optimizers for an iteration of 40,000, the results that was obtained has been shown here. Now it can be seen that a good agreement of has been predicted for the exact solution S of x, which is the first graph. However, the predicted residual ds, the derivative of S of x, which is u of x, shows that there's a large approximation error. And there's a large approximation error. This could be due to the non-smoothness of the rectified linear units function. The same experiment was carried out with tan-h activation function, keeping the same hyperparameter settings. And despite, we could observe poor predictions. Despite the guarantee of universal approximation theorems for operators, it is possible that DeepOnet models may predict output functions that are not compatible with the ground truth operator that generated the training data, as could be seen through these outputs. Now, the same problem would be solved using physics-informed DeepOnet, but I'll first explain the architecture. So here, the solution that has been the DeepOnet, physics-informed DeepOnet is basically the integration of physics-informed network in the DeepOnet model, where like the physics-informed networks, neural networks can seamlessly integrate the data measurements and the physical governing laws by penalizing residuals of the PDEs in the loss function of a neural network using automatic differentiation. Now, this concept has been motivated from pins, and the idea of DeepOnet basically involves the integration of in the loss function, it involves the integration of the physics-informed loss, the boundary loss, and the initial condition loss. While physics-informed loss is basically the minimization of the residual, the boundary loss and the initial condition loss are basically the data-driven losses. But we do not require any input-output data set as required in DeepOnet. Now, the same problem has been, the antiderivative problem has been studied for this architecture, where in the previous architecture, 2 hidden layers were used. Here, 5 hidden layers with 50 neurons have been used with tan-h activation function. The optimizer is the Adam optimizer with 40,000 epochs. In the table, we can see that the physics-informed DeepOnet with tan-h activation function, the relative error for S and also for the derivative of S, which is U, is much lower than the than the solution obtained from the DeepOnet for the rectified linear units and tan-h activation function. Now, this has been obtained using 1,000 samples in the test data. So to achieve the same accuracy level as physics-informed DeepOnet, the conventional DeepOnet requires 10 times the training data. And the training time for DeepOnet was 0.03 hours, and for the PI-DeepOnet was higher. So it is said that because we need to satisfy the physical laws, so the time required is higher, and the time was computed on the same system in the single NVIDIA V100 GPU. These are the convergence plot. So the convergence plot for the DeepOnet model for the rectified linear units and tan-h has been shown. So tan-h has rectified linear units has a much lower loss than tan-h. Here, the individual since physics-informed DeepOnet involves the physical involves a loss due to the physics and due to the boundary condition, where the where the loss from the operator means the boundary losses and the initial condition loss and the physics loss. So both of them have been shown here, and the results for one representative input sample from the test data set. Now, the data that was generated, now we'll study the same example using regular inputs, where in the previous sample, we had sampled T in the domain 0 and 1. And here, the sensor points are on the branch net are equispaced grid points in the interval 0 and 1. And the loss function is a similar loss function where basically we have an operator loss and the physics loss. The operator loss is defined as the initial condition and the boundary condition loss, and the physics loss is the residual loss. in this also, it has shown that DeepOnet, the individual DeepOnet model cannot go up to the error level as the physics informed DeepOnet for both S and the derivative of S, that is U. Now, these are the solutions that are obtained using the first set of solutions are obtained using using DeepOnet with tanh activation function, and it shows that the conventional DeepOnet learns. It seems that the conventional DeepOnet learns a degenerate map that can fit only the initial condition at S0 is equal to 0. But when it comes for predictions at higher x, like at x greater than 0, the model is unable to learn it and predict it. Whereas the predicted solutions of S of x and the corresponding residuals have been predicted pretty well by the physics-informed DeepOnet. Here, the one-dimensional ODE, or the same antiderivative problem, has been solved with irregular inputs, where the physics-informed DeepOnet can accommodate extremely irregular input functions by using appropriate trunk network architecture. Now, to illustrate this, a Gaussian random field with a prior L is equal to 0.01 on the input function space is used, and 200 sensors are used and the same data generation procedure is repeated. In this example, the training data set is 10,000 for different U samples, while the test data set is 1,000 realization, same as the previous one. Now, given the input functions from a Gaussian random field with a relatively small length scale, the associated solutions are expected to exhibit high frequencies. And because of that, Fourier feature embeddings have been used to be able to learn the high frequency components, and that would be more effective. Now, in this, the network architecture that is used is 5 hidden layers with 200 neurons each and tanh activation function. The optimizer is Adam, and 300,000 epochs have been used. We can see that the predicted results are matches the exact solution. Now, the same problem was repeated without the Fourier network, without the Fourier feature embedding, and we could see that the physics-informed DeepOnet was unable to make accurate predictions. So the same network, the same architecture was followed, but without the Fourier embedding for high frequencies, it was unable to capture the results. Now, the data that was generated used a prior of L is equal to 0.01. Now, what is tried is that the test data was generated with a Gaussian random field with a prior of L is equal to 0.2, and it could be seen that the neural network can make accurate predictions even for out of distribution examples. Now, this is a diffusion reaction equation, where they tried to solve the diffusion reaction equation, which is defined as the partial derivative of S with respect to t is equal to the diffusion coefficient times the double derivative of S with respect to x plus the reaction rate times S squared plus U of x, where x and t are defined on the domain 0 and 1. Now, they have 0 initial and boundary condition. The aim of this method of this example was to learn the solution operator for mapping the source terms U of x to the corresponding PDE solutions S of x using the physics-informed DeepOnet. And here 5 hidden layers with 50 neurons each and tanh activation function has been used. The Adam optimizer with 120,000 iterations, and there are equispace sensors of 100 equispace sensors in 0 and 1 in the interval of 0 and 1 is used. Now, we could see here that using the DeepOnet model with tanh and rectified linear unit activation function, we could achieve.
Excuse me. Hello, this is Lulu. Excuse me. Should here there's minus U, right? So makes minus U here.
Okay.
It is right.
I think you're right. Yeah.
Okay. Yeah. Okay. Thank you.
Yes. Sorry.
Hello, this is Ehsan. Can I make a comment? They actually added in the next line. So if you look at the next line, so they have the r theta minus ui in the double summation that they have.
Can you tell, Esan, I couldn't follow you. Could you tell me again, please?
So look at the very last line.
Yeah. Oh yeah, here there is U.
Yeah, they actually add the UI here. Yes.
Yes. Yes.
So they are not missing that term.
Yeah. Sorry. So, yeah. So the trainable parameters were obtained by minimizing the loss function. The physics informed this is a combination of the physics informed loss and the data driven loss because it had zero initial and boundary conditions. So these are the results, the exact solution versus the prediction of the trained physics informed DeepOnet has been shown here. They have made a comparative study of using different activation functions and the physics informed DeepOnet using the tanh activation function. It is shown here that the physics informed DeepOnet yields 80% improvement in the prediction accuracy with 100% reduction in the test data size because no data was required apart from the boundary condition. And these are the mean and the standard deviation of the errors that was obtained. Now, using this this example, actually we used to make a small validation of the work. So we generated the random field using the Gaussian random field. This will be U of X. I'm sorry, this won't be S of X, it will be U of X. So the same diffusion equation was solved and we obtained the test data, the mean and the standard deviation of the test data as which is similar to there is like 0.42% and the sigma was 0.175%. We followed similar architecture. Next, they solved the Burgers equation.
Somdatta, let me, can I, because everything looks simple and it's not that simple. Can you go back to a couple of slides? No, the history loss, a couple of slides, not the history loss in this example. In the same example, the diffusion here. Yeah, you see the loss of DeepOnet, right? And look at the rate, right? So and look at the time. So you train these, or the Paris did, for half the time. So if you go to the next one, you see that you check your times here, 1.3, 2.17, which is exactly the half, right? So imagine, go back now, one. Imagine you train DeepOnet for another 10 to the 5th, right? Which is the time, 10 to the 5th. Then that's for the same time, because you see the slope of the history loss, of the history of the loss here is very steep compared to physics informed.
Yes. Actually, that is what they said, that they require more time to solve the physics informed DeepOnet.
No, I know, but to make a fair comparison, if you continue training DeepOnet for another hour and 13 minutes, whatever it is, then you compare then I want to compare the accuracy. Okay. Or equivalently, if you have more samples for the same time, so you need to match the time to make a fair comparison.
Yes.
And what I'm saying is, looking at the loss and the history and the slope, I can tell you that the factor of 2 that is gained with PI-DeepOnet may not be a factor of 2 if you actually match the time cost also. It may be even. But anyway, continue.
Can I add something here?
Yes, Raj.
Yeah, and with less memory also, because you are training it on GPU, because for residual points, you need more memory also. So
yes.
You can add more samples in the DeepOnet. So.
Okay, thanks. Go ahead.
Okay, now they solved the same, using the same network, using the physics informed DeepOnet. They solved the Burgers equation This equation was actually solved to highlight the ability of the proposed framework to handle nonlinearity in the governing partial differential equation. Now, this equation, apart from having the initial boundary condition, also has associated periodic boundary conditions, where the time in this equation, the time is varying from 0 to 1, and the viscosity parameter has been taken as 0.01. The initial condition u of x is generated using a Gaussian random field satisfying the periodic boundary conditions. And the solution operator is approximated by the physics-informed DeepONet, g of theta. And then for a specific input u of I, x of I, these are the loss functions and the residuals. Here, P and Q are equal to 100 and 2500 respectively. Now, the synthetic data has been generated using the Chef1 package with a spectral Fourier discretization and a fourth order time stepping scheme with a time step size of 10 to the power minus 4. 7 hidden layers with 100 neurons have been used, and a tiny activation function is used. The optimizer is Adam optimizer, and 200,000 epochs it was trained for 200,000 epochs. Now, from this result, you can see that the predicted solution of a trained physics-informed DeepONet doesn't match the input condition, and the relative L2 error is 1.7 times 0.017. So there's a discrepancy. Now, to alleviate this, what they do is they propose improved multi-layer perceptron architecture, which is more powerful, and also they use a regularization parameter with the initial condition. Now, lambda has been taken as 20 here with a relative L2, and now after doing that, they have the resulting relative L2 error is 3.1 times 10 to the power minus 2. And we see that the input sample and the predicted sample, they have very less error.
So what's the architecture in the branch now?
No, they remain the same. They say they have used a improved architecture, which is of the form. I'll show it to you.
Improved is relative.
I don't know how to.
Can you just describe it, please? Just describe it. What is it?
So basically, the forward pass has has been modified, where they are using like in this architecture, the parameters of the model are essentially the same as the fully connected network, but they have added additional weights and biases into transformed network system. Like this is basically the network architecture that they are following.
Okay.
And now they have shown that using the modified multi-layer perceptron and the individual, the fully connected neural network. So they say that the relative L2 error is way lower for the modified MLP. And also they have provided a time comparison along with a relative L2 error comparison, which they say that the trained physics-informed DeepONet model can predict the solution with 10 to the power 3 like for a complexity of 10 to the power 3 time dependent PDEs in a fraction of second, which is 3 orders fast, magnitude fast.
Why don't they compare here with DeepONet?
They did not.
Why?
I didn't see the result.
But why? Do you know why?
I think because...
we should ask them. I don't know if Sifan or Paris are here, but we should ask them. I know the answer. Like, for example, let's say I solve the Euler equation, right? We use DeepONet. We use simulations from WENO to get the shocks for the Euler equation with chemistry, right? How can you do that with pins? Because you have to solve the forward problem, so we'll not do a good job. So it's one-sided. I don't know why they don't balance their criticism. Here, I'm sure that if you have solutions of obtained, let's say, with another scheme, and you feed the DeepONet will do a good job. But PI-DeepONet does not do a good job. Not a fair comparison, but keep going.
Now this is the last example, which which is shown, which highlights the capability of the proposed physics-informed DeepONet to handle different kind of input functions. So here, basically, they have used two kind of input function. One is the case one where they study the parametric circles, and also they study parametric foil. So we'll first understand what this is basically an equation where this is the equation where x denotes the two-dimensional spatial coordinates, and omega, the domain, is an open domain with piecewise boundary condition. A solution to the above equation is a signed distance function which quantifies the distance of a point in the domain to the boundary. Now this was actually the reason why this was done using for the parametric circles, to study the parametric circles, is that the sine function could be easily represented as the equation of the circle, and where the center is at 0, 0, at 0, 0. And here in this, the network architecture has 6 hidden layers with 50 neurons each and a tanh activation function. The optimizer is the Adam optimizer, and number of epochs was 80,000. So we could see that the predicted results, the absolute error is 0.4%, and the loss function goes down to 10 to the power minus 5, the operator loss. And the last case considered is somewhat complex, where they parameterize the curves corresponding to the airfoils of different shapes. To obtain that, the training and the test data, they use the UIUC airfoil data site, and which contains a total of 1,552 airfoil geometries. Now the first 1,000 shapes are used as training data, and the rest was used at the 552 data was used as the test data. Here they have used 6 hidden layers with 100 neurons and an exponentially linear unit activation function. Adam optimizer with 120,000 epochs has been used, and if we see the results, the top results basically they are the exact geometry or the input sample that has been shown versus the zero level set obtained from the predicted sign distant function for 3 different input samples has been shown. And the bottom line shows basically the signed distant function for it obtained from the trained physics informed DeepONet for the same 3 input samples in the test data. Now, they have left the paper with 3 open questions. I already told you about the benefits of it. And the open questions are that what are the optimal features embedding the network architecture for the physics informed DeepONet? What would be the appropriate weights to be used for training the physics informed DeepONet? And how to design effective algorithms for accelerating the training and ensuring accuracy and robustness? Now, before I end the presentation, there was one thing which I also felt was not a fair comparison, was in the first example where they have shown the antiderivative example. They have used the DeepONet with two hidden layers with 50 neurons each, whereas for the physics informed DeepONet, they have used 5 hidden layers with 50 neurons each. So basically, the depth of the neural network was much higher. So I felt that could be a reason, but I didn't get time to like redo it and check it. I think with that, I end my presentation.
All right.
Okay,
Thank you, Somdatta. Is there any other questions?
Lulu, do you have any response?
No. Yeah. Yes, the idea actually is the combine the PI and DeepONet. It's a 3-step.
Oh, can you hear me?
Yeah, I can hear you.
Hi. Oh, hi, this is Romulo from Brazil. I would like just to comment about the last example with the economic equation. Well, maybe 80% of the audience had the same idea, but it seems interesting to use for at least two things, like as an alternative for the pointwise weighting for the residual part of the loss function, like the guys from NVIDIA do on SimNet. You could use the sign distance function for that. And also, I have no idea if you have better ways of doing that for movable boundary problem. Oh, I'm sorry. Okay, can you still hear me?
Yes, now I can hear you.
Oh, okay, sorry. And for problems with movable boundaries like simulation of windmills, like guys that use finite elements need to struggle with remeshing and I don't know, adaptivity and those kind of stuffs. But maybe this could be kind of plugged into a PIN framework to do simulations with movable things, even like for a flow around a cylinder. Maybe you could parameterize geometry using the sign distance function. I just wanted to point that out.
Okay. Yeah.
Yeah, that's a good suggestion. Of course, either form of DeepONet will do that. It doesn't really matter. This idea was proposed in our DARPA project by Lulu, but we never published the paper, anything. So, but this idea, this parametric geometry was also proposed for pins by I forgot the name of the guy from Notre Dame who gave a talk here. Anybody remembers him?
Jiexun Wang.
Yes, Jiexun Wang. Yeah.
Oh, so you already have something about parameterized geometry for movable boundaries?
And it's not our work, it's somebody from Notre Dame, but he did it for pins. This is in the context of DeepONet, which is of course more generalizable, yeah.
Okay, because also I once saw a work from, I think it's from Raisi, and I think there was a flow around the cylinder, and there was a degree of freedom in the vertical axis. And I have no idea how he managed to do that, but I was thinking about the sign distance function. Okay.
I have a comment about the comparisons that we're making too, and something that kept resonating in my mind in their formulation, that they kept defining the data part of their loss function for the physics-informed DeepONet only using some usually simple boundary conditions. So they were saying we use no data because they were solidly defining the boundary condition there. But it will be a more fair comparison, and even also more open on their way, that instead of working on not working on the whole domain up to the initial conditions and giving the information sort of like an inverse problem. So give points inside of the domains for each different U in a way like the same way like the DeepOnets are trained. So that way you can really show the impact of adding physics regularization, but on the same kind of data. And instead of fixing all the time their data parts. Am I being clear?
Yeah. All the problems were pretty simple and had like mostly zero initial boundary conditions.
Yeah, and so the kind of data they were using to train one or the other was not the same then. It can be tricky then if how well you're training one or the other. What's the impact of the new terms in your loss function? It's not clear, it gets lost because you're not using the same data.
Yeah.
Good point, Patricia. Yeah. Any more questions? There's lots of people who are interested in DeepOnets here. Chazi from PNNL, do you have any questions?
No, I'm still reading this paper.
I mean, the other thing that is lost in this discussion is you don't have to do one or the other. A true PIN is like you do a little bit of data, a little bit of physics, right? So it can be run as a true PIN. Here they're trying to do just the equation for these Mickey Mouse problems, because for example, in our work with the multiscale operator, some of the data is from the Rayleigh-Plessé equation, which is a PDE. Some of the data comes from MD. How would you how would you incorporate MD into the loss function? You're doomed. so it's a little kind of, I don't know why Paris did that, but he didn't show up today to tell us why he didn't do that. Right? If you have MD data feeding like an MD type atoms, how would you actually incorporate that into a pin? Of course, if you have the continuum part, yeah, you can write it. But somewhere, as I see, this is actually, for those of you who are using DeepOnets and try some sort of a hybrid model where you incorporate some of the physics and some of the data could be, and of course, all the other features, that the Fourier features and so on, that's problem dependent. That could help. That's kind of my opinion. Sanjay, do you have any comments? Sanjay is working a lot with.
No, I don't have any comment. No.
Questions for Somdatta?
Can I ask a question?
Yeah, of course, Yan John.
Yeah, this is Yan Jong. Hi. I remember one of the slides showing that DeepONet with the hyperbolic tonnage seems not working properly.
Yeah, I'll show it to you.
I wonder why I wonder why. Do they?
Antiderivative problem.
Or Lulu can answer or have some ideas?
Yeah.
Yeah, Lulu did it, so Lulu should answer.
Yeah, this one.
Why
So
is that
actually,
the case?
Yeah, for the activation function, actually it's problem dependent. For example, for the fractional case, the Guofei did, and for that case, he found that the tangent edge is better than Relu.
Have you ever tried the ReLU power, the case power of the ReLU? Because it feels like if the it seems to me that if the ReLU performs well, but in the case where you need some smoothness on the top of it, then actually the ReLU case power actually is working great. So that I think if someone who working on DeepONet may want to implement it with the case power of the ReLU, like 2 or 3, I think that would be good enough. And if I'm expecting that if that is the case, I think the example that is presented here, the tonnage versus ReLU, I think the ReLU case power might be working similarly to ReLU just ReLU part.
Yes,
Somdatta can try. Somdatta, can you try? Because Somdatta is working on that now. So maybe Somdatta can try it, Young John's suggestion.
Yes, I think you made right. So I have seen a few papers using the ReLU to the power, and it works really well.
Right, and especially for the fractional PDE, that you can actually match the fractional part to the exponent. The K can be just any number. So,
oh, I see. You can have a fractional power in the ReLU.
Yeah, exactly.
Oh, I see. That's really interesting.
So actually, I have tried some like toy examples that I realized that, oh, wait a minute, I can use the fractional order.
Yeah.
So that it turns out I can a little bit matching things up so that find some good matches. Like for example, for L-shaped the Poisson equation, then you have some singularity and the expression, the analytical solution has them raising the power, like R to the like 2/3 and so forth. And if you actually matching some of the power corresponding to that, actually, you can gain a little bit more.
Yeah, that's a good idea.
Yeah, so actually that is there's a room for, I believe DeepONet can be more efficiently trained by a little bit controlling the ReLU's the case power. And if you need some theoretical backup, then we can always rely on Jin Chao's work.
Right. I was thinking, Exam, can you try that? Can you just investigate in a simple fractional problem or the COVID or something?
Sure. We can do it. Yeah, but we didn't use the DeepONet, right? So you mean for the FPIN?
No, it doesn't matter. Yeah.
Yeah, it doesn't matter. Yeah, really. But be
Okay,
careful. But
yeah.
be careful about the choice of the P. If you use some more power or the poorly chosen P and you do some more derivative, then actually the sum of the part become negative, the exponent become negative, then you occur some singularity. So that, yeah.
Okay.
That's a
By
good
P, you mean
suggestion.
the exponent. By P, you mean the exponent of ReLU?
Yeah, K. So for example, if your PDE involved like the double derivative involved, then you don't want to use the K equal to 2, or probably you need to use the K equal to 3 because the back propagation needs 2 plus 1. So that, but any number is fine. You can use the fractional one or square root of 2. I'm not sure how numerically it can be done, but the main point is you can use the fractional order in the kth power.
Okay, I see. Yeah.
Great.
Can I ask a question to Somdatta? I just look at this paper as curious whether they provide any comparison to like a standard pin, just using the feed-forward neural network.
No, they haven't shown any comparison with the conventional pins.
Because it seems to me it's very just similar to the previous pin framework. I'm just curious what we can gain from this DeepONet architecture for this kind of problem solving PDEs.
They have shown actually numerous, what they are saying with DeepONet and DeepONet inform, like physics informed DeepONet and just DeepONet, saying that they have gained on accuracy where the magnitude of like the error has gone down, and also they're using some extrapolation and they've shown the examples using saying that they can the physics informed DeepONet can predict the extrapolated function tasks, and that is how they have shown, but they haven't shown any comparison with the conventional physics informed DeepONet. And actually I'm working on a similar problem for fracture, so maybe if I get it, I'll definitely try and show it.
Okay, thank you.
Jeremy, do you want to say anything? You wrote an N in the chat. What does it mean, N? No? Or maybe I didn't, yeah. Jeremy?
I probably just hit my keyboard on accident. No, I didn't want to say anything.
All right. Right. Anything else? I think back to you, Minlang.
All right, so let's thank our speaker again. And this is the end of our this week's Crunch Group seminar. Thank you for attending this. So I'll see you next week.
All right. Bye-bye. Thanks.
Bye.